Nothing really slow. No, I turned it off. It was on, I think. And it's not responding. Still not responding. Yeah, once you get used to this big delay, lose your anxiety over whether it's actually going to eventually respond. It's not that long to delay. As soon as I get used to it, then I'm going to expect it next time. Okay, so you get, anyhow, you have an electric field like this, it's going to attract, so it's going to pull the negative charge this way. Pull that up one. Pull this up two. Okay. So we'll just say that, okay, that's negative QE. And this is QE. Let's say that this thing is at some angle. Some angle theta. Then what's the torque? I'm gonna let you work on that. Not long because I don't want to struggle with Zoom. Just quickly write out what you can say about torque. I'm going to leave the camera on. When I'm talking about Zoom, I should be talking probably about our internet connection. Slow this down. Could be even. How do you get that torque? Okay. Maybe. Can't tell exactly what you're thinking, but let's look. Okay. Well, torque is the sum of your R cross F, right? Now, intuitively, I want to think about this intuitively. Now, first of all, what's your R vector? We're going to say, I haven't given you length there, and you can't answer the question without a length. Okay. So what I saw is pretty much what I hoped to see. Okay. Length is going to be 2A. Which is convenient because now your R vector here your R1 and your F1, right? Now, just to review, this is going to tend to rotate counterclockwise, right? I got something fixed here. And a force acting out here, it's going to tend to rotate the bar, or whatever it is, this way. And by the right-hand rule, if you just rotate this way, your force is here. Or if you do R cross F1, your force is here. So it's R cross F1, or R cross F, not F cross R. Okay. If you want to resolve that. Just ask yourself, take an example. Okay, here's a R vector, here's a force vector. Is it rotated clockwise or counterclockwise? Then the right-hand rule has to be consistent. It's rotating, you put your fingers in the direction of rotation, you get the direction of your torque, right? But if you do R cross F1, you get the same thing. If you think it's F1 cross R, you're going to get the opposite thing. So there's two ideas. It's the right hand. Yeah, I think you're doing pretty well with that. Okay, so we got R1, we got F1. Okay, then we got R2. And F2. Okay, and R2 cross F2 also tends to rotate it counterclockwise. In other words, these two forces are going to join and tend to make it rotate. So the magnitude of your torque, without writing this out, well, first torque is R1 cross F1, second torque R2 cross F2. The magnitude of both of these torques. If this angle is theta, then that's also the angle between R1 and F1. It's also the angle between R2 and F2. Okay. And you remember the cross product has a magnitude just equal to the product of the two magnitudes. Okay, I'm just trying to say. That turns out to be F1A sine theta, right? Down here. Let's say tau equals this. That's tau without the arrow. Tau 1. R2 F2 sine theta. Same direction. But of course, that's just F2A sine theta. F1 equals F2. Now vector F1 doesn't equal vector F2 because they're opposite directions. But by just saying F1 and F2, I'm talking about the magnitudes of the vectors. But I'll go ahead and do something that's not totally necessary, but I'll whatever else I'll from the magnitudes of that, right? Found out is found out is 2AF sine theta. The vector is bound by the right-hand rule. Okay. And now we want to say I should look and see what symbol they use. I'm going to use mu. I think it's standard symbol. If it's wrong, I'll replace the symbol right now. Cross product of mu with E. For mu equals A. I'm not even sure that's totally right. I should have looked at it. Or I did this. This is the idea. It's just something you can cross with the electric field to get the torque. And you don't have to worry about all the details. So like if you're trying to look at the dipole moment of an atom, you know what the charges are, but not really, because the electron charge is distributed over sort of a cloud. Okay, almost a cloud of charge. And if the electron charge is because of some electric field pulled away from the nucleus, so that the cloud, which is ordinarily centered at the nucleus, is offset just a little bit. Now you've got magnetic moment. I mean a dipole. Okay, so then you can talk about how that responds, or whatever electric field, or if you have like a van der Waals force or something like that, and we're not going into detail. Somehow, a charge distribution in a polyatomic molecule is 5%. Okay. You can get a dipole moment out of that, but you can't measure the dimensions. You can infer the dimensions if you can somehow measure the dipole moment. Opposing electric field, see what that does to the energy level. Okay. And you know, that's off the top of my head. I think we should do something along those lines. I've never done that. I just want to look and make sure. You know, I'm having a problem. I don't like that too. Their definition. This is supposed to be the length of this. Would have room to completely drop about liberating stuff. There's D. Now, D, you multiply D by the unit vector of the direction from the negative toward the positive charge. Okay, so see their definition. I'm going to pause Zoom long enough to give myself time to take a look. Make sure I've got it right. Did it ever say it was recording? Yeah, my hearing aid was turned off. I don't know why I didn't hear it. Okay, that was right. So they don't put an arrow over that. That's garbage. It's the vector I want to do. It's got to be across the point. Okay. Some know what they tell you. Okay. Yeah. Almost forgot that they do things like find the field due to ring of charge. Okay. And they do a line of charge. Give you a quick synopsis. If you got a ring, so this is a ring down like that. X, Y, a circle. Radius A. Total charge. Now, this kind of goes along with what we did in about curvature in multivariable calculus. We have to partition variable and so forth. You partition this circle. And then you pick a typical interval. Now, within this interval, how much charge do you have? Well, this interval has let's say length delta S. And it holds charge. Delta S over 2 pi r, right? Because circumference is 2 pi r, there's a delta S over 2 pi r of the entire circumference. Of course, minus Q. Now, let's say that we want the field at the center of this ring. Well, if we just assume this is a very small interval, because of course we're going to ultimately we would do an interval where we shrink all the intervals down, you know, to the limit of 0. Okay. So now we have charge. Two delta S over 2 pi A. There's our charge. Here's our vector, center of the surface. has magnitude A. Okay, so the okay, I've got to back up. I should have talked about it first. We're talking about calculating the field. We assume there's a test charge at the center. Okay. Force or charge Q at the center is then going to be kind of mixing up my use of capital lowercase q. So I think we'll put that up. It's just your K times this charge times this charge. Okay. At the center, that's over R squared. Times your R hat. Your different vector. Okay, so it's a vector in this direction with this magnitude. Okay. So that's good. Now, let's just say you set up your partition so that on the opposite side of the center, there's an equal interval. Its charge is the same as this, right? So it exerts a force in the opposite direction. And you can say the same for any interval, so that by the symmetry of this thing, there's zero force at the center. Okay. Now, it gets more interesting if you want to find the force at a point of the z-axis. That's the point 0, 0, z. Then the force exerted by this charge here will be a vector, maybe here. Okay. And the force exerted by the charge here will be another vector of the same length, same magnitude, because it's the same distance. Okay, and at the same angle with the z-axis, but in the same plane as these two. Okay, which means that these vectors solve into components like so. Then the angle, you can figure out what the angle is. You got a right triangle from here to here to here. The hypotenuse is z, this side is a, so this is squared of z squared plus a squared, all that stuff. You find an angle, you can find the components. These two components cancel, these two components reinforce. Their net force is like this. It's the same for every pair. The net force is along the z-axis, they all add up. Okay. Now there are other problems, but I don't have time to anticipate. That involve like a bar with charge on it. Okay. And maybe another bar with charge on it. How much force does this bar exert on that bar? Well, take an increment of this one and an increment of that one and figure out how much force the charge in this increment exerts on that increment. And you sum it all up. And it's just basic first year calculus, but in an application that's probably going to cause you to have some questions. Try to talk about that a little bit more. Although we want to actually get our hands on this stuff. Okay. Since we just might make that little sacrifice, half hour lab to talk about that. Fair enough. Please get into the assignment before that. It'll make more sense to you, what we do in the lab. And of course, and everything reinforces each other nicely. There's a lot of stuff in the assignment. It's a long assignment. It's just one per week. So you want to start them early in the week. So walk in front.